Alright, here we go with the Chapter 2 Homework 1 review, the second one of these for this semester. The average on this one was a little bit lower, so in case you're curious about how we did, the average score for all people that did this, in this section anyway, was 10.4 out of 12, so still not bad overall. Now I do want to point out that some of this lower average is probably our fault, or my fault, I guess, because of the snow day that we had earlier, we weren't quite caught up, and there was a couple of homework questions on this assignment that we haven't actually covered in class yet. So sorry about that happening. If you think this is a grave injustice, just keep in mind that we do drop your two lowest homework scores, and the homework is only 6% of your grade, so a couple homework questions here or there is not going to really affect you in the long run. So please keep that in mind before you show up at my office with pitchforks. So a couple of those questions that we had trouble with, I guess, are things that we will see in class today, and we will get caught up today in class. This won't be an issue the rest of the semester, provided we don't have any more unexpected cancellations. So we're going to get caught up today, and then next week, this week's homework assignment, one that's due next Sunday, is going to be another one of dealing with Chapter 2 material, so you will get a chance to review some of this stuff, even if you felt like you were totally lost on this assignment. Alright, so with that, let's get into the questions, and I'm only going to cover questions on this homework assignment that we already dealt with in class, so some of the other ones I'll push off until next week. So the first couple are conceptual questions about the Bohr model. We didn't do terribly on these ones, but I just want to make sure that we're clear on this. So it's one of these types of questions: which statement is not true of Bohr's model of the atom? So before I go through all the answer choices, remember that the Bohr model states that you have your nucleus at the center, and then you have these circular orbits around. I'll try my best to draw actual circles here. So they're all circular orbits that go around the nucleus. And as you go further away from the nucleus, you have these different quantum numbers that define each orbit. N equals 1, N equals 2, N equals 3, and so on. And each successive value of N is a higher energy level. And then when the electron stays in the same orbit or the same energy level, the energy of the atom is constant. But then if it wants to move between energy levels, it either has to absorb a photon to go to a higher level, or it has to emit a photon to come down to the lower level. So that's basically what the Bohr model says. So let's see which of these answer choices is not true according to that model. So the first one, A. Bohr's model correctly described the atomic spectra of hydrogen and helium but failed for other atoms. This one is almost true, but not quite true, because the Bohr model only works for one electron systems. So that's another key component of it that we've discussed in class now a few times, is that the Bohr model only applies to one electron systems, which means the only neutral atom that the Bohr model works for is hydrogen, but it won't work even for helium, which only has 2 electrons. So it would work for helium plus 1, which is helium with only 1 electron and a net positive charge. But this one would only work for hydrogen, so this is going to be the one that's not true. So this is likely our answer choice, but we do want to still go through the rest of these to make sure. So choice B, an electron does not radiate energy while in a stationary state. I haven't used the term stationary state yet, but this basically means in a set orbit. So stationary state is an energy level or an orbit for an electron, whichever terminology you're using. And so that's something that is going to be also true. It won't change energy, it won't give off energy as long as it stays in the same orbit. C, an electron can move to a different orbit only by absorbing or emitting a photon. So this one's going to be true as well. This one's going to be true because that's what we just talked about. If it's going to change from one orbit to another, from one stationary state to another, it has to either absorb a photon to go to higher energy or emit a photon if it goes to lower energy. The energy of a photon absorbed or emitted by an electron is equal to the difference between two energy states. This is also true. In other words, the photon that is involved in this process of going between energy levels has an energy that's exactly equal to the difference in those energy levels. You can think of that as conservation of energy. If the electron is gaining a certain amount of energy or losing a certain amount of energy, that energy has to come from a photon or go to a photon. So this one's also true, and this is kind of the concept that is going to come up in some of the numerical problems we'll talk about in a few minutes. And then finally, the last one, electrons in stationary states in the Bohr hydrogen atom occupied circular orbits. And so this is another key part of the model, as we said, this idea of electrons going in purely circular orbits, which is physically not true, but it is part of this model, and this model still is accurate for many other aspects of the hydrogen atom, just not correctly describing this. So this is a true statement according to the Bohr model, even though it's not a true statement in the more complex model, quantum mechanical model that we talked about later. All right, so we just want to make sure we understand these concepts, and I'm going to take a quick pause here before I go on to the next one. All right, we're back. Sorry, sometimes I get sidetracked when I'm doing this in my office, so I'll have to take occasional breaks. All right, the next one is another conceptual question dealing with quantum numbers in the Bohr model. It says, which of the following is not determined by the principal quantum number n of the electron in a hydrogen atom? So the principal quantum number n is the only one that we see in the Bohr model. And so in the Bohr model, and really in general, it tells us the energy of the electron. So as we talked about in the last problem, if you have higher value of n, the electron is at a higher energy level. And then finally, the other thing that it tells us is the radius of the orbit for the Bohr model. So I should say this is true of the Bohr model. Now, if we're talking about the hydrogen atom, for the quantum mechanical model, the quantum number n has a very similar definition, or tells us very similar things. N still is the only thing we need to determine the energy. So if you only have one electron, and we're dealing with hydrogen here, so we do only have one electron, then n is exclusively going to determine the energy. We don't need any other quantum numbers to determine energy. And then it's also related to the size of the orbital. And by size of an orbital, remember that an orbital does not have a specific radius or a specific orbit associated with it, but it does give us the probability of finding an electron in a certain volume. So either the most probable radius becomes larger if the value of n comes larger, or the total volume of the orbital that encompasses 90% probability, or whatever you choose to define, also becomes larger. So really, whether you're talking about the Bohr model or the quantum mechanical model, the value of n tells you this roughly the same thing in both cases, or at least qualitatively it does, which is the energy of the electron is determined by n for a hydrogen atom, and then the distance of the electron from the nucleus is determined also by the value of n. Alright, so let's look at these answer choices. We're looking for the one that is not determined by n. So the energy of the electron is going to be determined by n, as we just said. The minimum wavelength of light needed to remove the electron. I don't really like this this answer choice here, the minimum wavelength. It really should be just the wavelength of light, or if anything, the maximum wavelength of light. But anyway, this one relates to the idea of if we shine light on the electron and it has high enough energy, it can completely remove the electron, and that's coming from the Bohr model, where delta E is equal to minus 2.18 times 10 to the minus 18 joules times 1 over final value of n squared minus 1 over the initial value of n squared. So this equation here is what is going to relate to this answer choice. And if nf goes to infinity, in other words, we get to an infinitely high value for this final n, what that means is that we're removing an electron completely. And so if we want to know what's the energy of the photon, or the corresponding wavelength of the photon to remove an electron, this one goes to infinity, but then we need to know what the initial value then is that we're starting with. So depending on which value of n we have initially, in other words, which orbit the electron is in, it's going to take different amounts of energy to remove that electron completely. So this one's also true, although I don't like how it's worded. It is going to be one of the true statements, and it's certainly not the worst of the statements. Now, C is the size of the corresponding orbitals. We talked about that in the Bohr model. It tells us the exact radius of the orbit. Even though that's not really true for the orbital model, it does still tell us the size of the orbital, or the most probable radius. and that's going to increase with the value of n. Now choice D, the shape of the corresponding atomic orbitals, this is the one that is not determined by the value of n. Remember, the shape of the corresponding atomic orbital is determined by L, which also has these letter designations S, P, D, and F. And so if you want to know the shape of the orbital, you need to know the second quantum number L, not just the principal quantum number. The principal quantum number does not tell you that by itself. And then E is all of the above, which clearly can't be the case. So choice D is the one that is not determined by the principal quantum number, the shape. As I said, I don't like how choice B was worded, but it is still related. And so choice D is the one that's clearly the incorrect statement. Okay, so those were a couple of conceptual questions that we need, to understand the Bohr model and understand some things about quantum numbers. Let's move on now to some numerical problems also related to the Bohr model. Again, I have to take a quick commercial break for something. Alright, we're back at it. And let's start some of these numerical problems. Alright, so this one is, what is the wavelength of light that is emitted when an excited electron in the hydrogen atom falls from n equals 5 to n equals 3? So this is a pretty straightforward or a pretty typical type of problem for the Bohr model. And remember that in these problems there's often going to be two steps involved. So the Bohr equation tells us the change in energy for that electron as it goes between these two different n values, 5 and 3. And that's given by this minus 2.18 times 10 to the minus 18 joules times 1 over nf squared minus 1 over ni squared. We talked about this equation conceptually in the previous one. And here we're going to use it to find the change in energy. Now keep in mind though, what the question is ultimately asking for us is the wavelength. So once we have that difference in energy, we have to be able to relate that to the energy of the photon that's involved, as well as then the wavelength of that photon. So there's going to be a couple additional steps here. But first let's apply this equation to find delta E. So we just put the numbers in. So if you want to get the sign of delta E correct, you need to have the n values in the correct order. It's not so critical for this problem because we're going to end up with a positive number at the end. So if you reverse the n values, you would just get the negative of that. Not a big deal. But let's make sure we put them in the right order. So we're going from 5 to 3, so that means the final value of n is 3 and the initial value is 5. So we're going to put the 3 there and the 5 there. And so when we calculate this out, I didn't even calculate this out yet, so give me a second here. We get a negative number, a negative delta E of minus 1.55 times 10 to the minus 19 joules. Keep in mind, I did leave out the z squared term here, z squared being the number of protons, but for hydrogen, z equals 1, so we don't really have to worry about that for hydrogen. And I think all of the homework and exam questions they give you are for hydrogen. I did mention there's that dependence on z in class, something just to make it more complete, but we won't really use that in these problems. So that's a quick thing I forgot. But anyway, we have this delta E value, which is negative because we're going from higher n to lower n. It should always be a negative number if you're starting at higher energy going to lower energy. And then from there we need the wavelength of light that is emitted. So this is the difference in energy between the two orbits, or the two energy levels. And remember that the energy of the photon is just equal to the absolute value of that energy. So if the energy is changing by minus 1.55 times 10 to the minus 19 joules, that means it's emitting a photon that has an energy equal to 1.55 times 10 to the minus 19 joules. The energy that is lost from the electron goes into generating a photon with that exact same energy. So that's the energy of the photon, and this is going to then equal hc over lambda, one of the two equations we have for energy of a photon. And so what we're going to do is just solve for lambda. Lambda is just equal to hc divided by the energy of the photon. And so we plug in numbers. H and c are fundamental constants that are on the periodic table that we give you, so you don't have to memorize them. And then finally we put the energy of the photon in there, the one that we calculated earlier, 1.55 times 10 to the minus 19 joules. Now we have to keep units in mind here, so that's going to be an answer in meters. So make sure when we're, especially when we're doing multiple choice questions, we make sure we have the units correct. And so what I got is 1.28 times 10 to the minus 6 meters. And we don't have to convert it because all of our answers are in meters, and this is the number that we get, B. Alright, so you'll notice that choice C is just the value of the energy, but with the wrong units. So if you had only done the first step, you may have picked choice C, and then these other ones likely would involve some miscalculation in one or more of the steps. But choice B is the one where we did both steps correctly. We converted, or we calculated the energy of the photon, and then we used that to determine this wavelength. So the next one is almost identical to this, just different values of n, but here we're looking for frequency in hertz. Now I didn't do an exact question like this in class, but what we have to remember for this problem is we're still going to use the Bohr equation because we need to find the energy difference, but once we have the energy of the photon, remember that there are really two ways to relate it. The simpler equation is actually just h times the frequency, but then we can also rewrite that as h times c over lambda. So we use the second form of this equation here in the previous problem, but this time we're going to use this form of the equation to convert energy into frequency. So it's again a separate step, but one that doesn't require us to do a whole lot of math. It's just dividing by a constant. So we're going to use the Bohr equation first to find delta E. Same exact equation. Keep the z squared term in here, so I forgot it last time. Again, it's not important because we're talking about hydrogen. So minus 2.18 times 10 to the minus 18 joules. Z is still 1, so we can just get rid of that. And then NF and NI is going from 4 to 2, so it's going to be 1 over 2 squared minus 1 over 4 squared. And this once again is going to be a negative number because we're going from a higher value of n. And so what I got for this was minus 4.09 times 10 to the minus 19 joules. So again, that's the delta E for the electron. The energy of the photon is just the absolute value of that. So it's going to emit a photon that has an energy of 4.09 times 10 to the minus 19 joules. And again, one of the answer choices is that number, but that doesn't represent the right quantity because this is the energy of the photon, but what we're looking for, to emphasize once again, is the frequency. So we need to do one more step. So that means mu is equal to the energy of the photon divided by h. And so we get 4.09 times 10 to the minus 19 joules divided by that constant 6.626 times 10 to the minus 34 joules second. Joules cancel out. We get an answer that's in inverse second or hertz, which is equivalent. So I'll calculate this out real quick. And what I got was 6.17 times 10 to the 14th seconds minus 1, which is the same as 6.17 times 10 to the 14th hertz. Alright, so remember that if you work it out, you're going to get inverse seconds as your unit. That means cycles per second or oscillations per second, and that we call hertz. So those are equivalent units. We don't have to convert anything. It's the same thing. Alright, so the only answer then that works is choice A. And so just make sure when you're doing these problems to look at what the question is asking for. It could ask you for the energy of the photon, it could ask you for the wavelength, it could ask you for the frequency, it could ask you for delta E for the electron. So all of those involve Bohr equation, but in many cases there's going to be a second step involved that allows us to convert that energy into the appropriate quantity. That's what we had to make sure we did here. Alright, so then there's two more we're going to do. The tablet is taking a break, so let's let it come back. Okay, so this one is another one dealing with the Bohr equation. It just wants to know which of the following energy levels is not possible in the Bohr hydrogen atom. So in this case, we're not talking about changes in energy. We're not talking about electrons moving between two energy levels. We're just talking about the energy of the electron in a stationary state in one of those orbits, n equals 1, n equals 2, n equals 3, and so on. And to remember that the energy, the absolute energy, is just given by that Bohr constant, minus 2.18 times 10 to the minus 18 joules, divided by n squared. So whatever the value of n is for that orbit is going to determine the energy level. If we're moving between those energy levels, we subtract the two values. So anyway, we have to just use this equation and solve for n, and keep in mind that for the Bohr model, or for any quantum mechanical model of the atom, n has to be an integer value. So it has to be 1, 2, 3, and so on. And so what we're going to do essentially for all of these answer choices is we're given the value of E, the energy level. We're going to solve for the value of n, and in order for this to be a possible energy level, n has to be an integer. So I think we did a question like this in class, but this is really the same concept. Just have to make sure that we solve for n and find which ones are or are not integers. So for choice A, so basically in each case we're going to rearrange and get n squared is equal to minus 2.18 times 10 to the minus 18 joules divided by whatever the energy level value is. So for A, n squared equals and then the given energy level is still that same thing. So n equals 1 for choice A. This would be the ground state energy level for hydrogen. So this is a possible value. This is the ground state value. So this one's okay. For choice B, we have 5.445 times 10 to the minus 19. We divide that by the Bohr constant, the ground state value. I reversed those, sorry. This should be the Bohr constant on top and the given energy on the bottom. Alright, so let me fix that. So that goes on top, the given energy level goes on the bottom. Get the algebra right. And so when we divide these two, we get 4, we take the square root of 4, and n equals 2. So this one's also an allowed energy level. It's the second orbit, or second energy level. For choice C, we have a few more of these to do. I'm not going to go through all the math. We're going to do the same thing. We're going to take minus 2.18 times 10 to the minus 18 and divide it by this number here. And so if when we do that for choice C, we get 9, which means n equals 3, also an integer value, also an allowed value. So that one works. For choice D, we get n squared is equal to 10, so this is just off by an order of magnitude from the Bohr constant. So when we divide those two, we get 10. And if we take the square root of that, n is going to be now a non-integer value. So the square root of 10 is about 3.16. This is clearly not an integer because it has a decimal after it. So this one is not an allowed energy value. It gives us a non-integer n value, so that can't be right. Let's check choice E to make sure that one works. So for choice E, when we divide the two, we get n squared equals, I believe it's 16. Let me double check that. I think I might have had a typo. This should be 19, sorry. That was the correct answer. I transcribed that one incorrectly. Let me double check. Yeah, that one should have been minus 19, not minus 18, so apologies for that. But when you do put the correct number in, you get n squared equals 16. square root of that is still a whole number 4, so this one works as well. And so the only answer choice that is correct is D. This is the one that is not possible because it gives us a non-integer value of n. Alright. And then finally the last one here is dealing with photoelectric effect, but it's really not even requiring us to know much about that concept. So the minimum energy needed to inject an electron from a sodium atom is 4.41 times 10 to the minus 19 joules. So if you remember from the photoelectric effect, we would have a metal surface, and then you're going to hit it with a photon, and in order for an electron to be ejected from the surface, you need to have some minimum energy or minimum frequency for the photon. So in class we introduced this as what we call the threshold frequency, which we abbreviated as mu sub 0. The other way of reporting this value or talking about it is what's called the work function, which is the corresponding minimum energy. Now, we still have the same relationships for energy and frequency, so E0, the work function, is equal to h times nu 0, which is then equal to hc over lambda. So if we know the minimum energy for the photon, we can convert that to a minimum frequency or to a maximum wavelength. So wavelength and energy are inversely related. So the wavelength that corresponds to the work function is the maximum wavelength that will eject an electron. Any wavelength smaller than that would also result in ejecting an electron. So all we need to do here is use the E equals hc over lambda equation, and what we're looking for though is the wavelength in nanometers. And I think a big part of the problem on this question was not using the equations correctly, it was just units, which is very often the case in general chemistry. So what we do is we solve for lambda, which is just going to be hc over E0. H and c are constants, so I won't write them out again, and then E0 is the given work function or threshold energy, 4.41 times 10 to the minus 19 joules. Now when we do this, we get an answer. Let me make sure I get the number right. So we get an answer of 4.51 times 10 to the minus 7. Now I know that many of you don't write your units out, and the very tempting and very easy thing to do is take the number that your calculator spits out, look for it in the answer choices, and circle it. So choice B here was the second most popular answer behind the correct one. However, we have to remember that this number here is in units because C here is in meters per second. I didn't write it out this time. But it's important to keep in mind what your units are. So when you use this equation and you use the standard values for these constants, you're going to get a wavelength in meters. This one wants it, though, in nanometers. So we have to convert that to nanometers by multiplying by 10 to the 9. So this would be 451 nanometers. So choice C is the correct one if you make sure that you keep the units right. So many of you picked B because that was the number that your calculator spit out, but that's a number in meters, not nanometers. Alright, so that takes us to the end. As I said, there's a few other questions that we'll go over next time related to electron configurations, which we're going to cover in class today. But if you have any additional questions on the homework assignment, please don't hesitate to contact me, and I will see you guys in class this week.